this is the apparatus over here, but I've got it all lined up and working pretty well. I've already done several trials before I started recording. And so I dug out another one here to take some of the preliminary measurements and just show you how it works. So basically what happens is I have here a sprayer with some mineral oil in it, and you squeeze the little bulb and it sprays a fine mist of oil that you couldn't even see in the video. Actually, you can't even see when you're here usually. That goes in through the little hole in the lid here, and down inside we have a set of parallel metal plates separated by a piece of plastic here. Inside that piece of plastic, I'm going to lift the top plate off. Inside the piece of plastic is, maybe I should get a real video camera where I can tell where I'm pointing it. I don't know how well that shows. Yeah, it shows up better like that. See, there's a hollow place in there, and some of the oil drops find their way down into that chamber. You can look into the end of the chamber through this microscope here. Okay, and there's a set of grid lines in the eyepiece of the microscope that give you some sort of reference points to judge the movement of the oil drops with. Now, these metal plates above and below the chamber can be connected to a power supply. Here, this is the power supply. I've got a meter on it so we know how many volts it's putting out, and the wires go on up, and that applies. It's going to, well, I'm sorry, there, okay. I roll it over a little. Going to apply, it looks like it's, for all practical purposes, it's exactly 263 volts. Jot that down somewhere. There isn't any printed answer sheet for this lab. Normally I have you print off something on the printer over there, but I'll get back to that. Just, you know, on the margin of the instructions or the back of your hand or something like that. Just note down that we have 263 volts. You can see it wanders a little bit, but usually not much more than a volt or so. I suppose I might as well leave that on. So applying that voltage to this set of plates creates an electric field in the space in between. These oil drops find themselves floating around in that electric field, and you see the oil drops pick up a little bit of a static charge as they come through the sprayer. More or less the same sort of thing that happens to you if you go scuffing your feet across a carpet on a dry day. You pick up a little bit of a static charge, and as they kind of scuff their way through the sprayer, a very small number of electrons gets transferred either to or from the oil drops. So they're floating around in there in this electric field, and I can control the electric field direction with this. Okay, it's kind of like a stick shift on a car. The neutral is in the middle, so when the handle is there, there is no electric field, and I push it to the one side, and that creates an electric field that points up. And I push it to the other side, and that creates an electric field that points down, a field of the same strength. Okay. What is the strength of the electric field? That's the first number we're going to need. Well, I've already showed you the voltage, and volts divided by meters gives you volts per meter. Okay, so how many meters, or how much of a meter is there between the upper and lower plate? Well, we'll just take out the spacer and measure how thick it is. There's the spacer in the caliper. That's in millimeters, 7.54 millimeters. So that gives you the strength of the electric field that our oil drops are going to be floating around in. And the calculations are all set up in a spreadsheet already. Of course, your job, you don't get off that easy. Your job when you write this up is you have to explain the calculations. You can be a little vague at a couple of points, but the first column spreadsheet is the strength of the electric field. And you can see it varies a little bit because like I said, the voltage tends to drift a little. And these first couple of trials I did a day or two ago, and I got slightly different results. But anyhow, that's how you get the field strength. Volts divided by meters gives you volts per meter. Volts per meter is equivalent to newtons per coulomb, if I haven't gotten that far in the lecture yet. So then, how do we find? Well, we're going to measure the charge on several oil drops. You can't just measure it on one, because if your objective is to determine the charge on an electron, how do you know the oil drop only picked up or lost one electron? This one over here has 3 units of charge. This one over here has 5 units of charge. This one is neutral. We better not use that one, and so on, okay? So you need to measure, well, if you were going to make a serious study and not just kind of look at this for a few hours in a freshman level physics lab, you would have to do dozens of oil drops to be sure you clearly saw the pattern. And you always make a few mistakes or things can happen, but most of the data, at least, ought to cluster around multiples of the elementary charge. 1.6 times 10 to the negative 19 coulombs. 1.6 times 2 is 3.2. 1.6 times 3 is 4.8. 1.6 times 4. Well, I suppose there's no reason I can't show you the results I've already got before I started recording. Scroll over to the last column on the spreadsheet. And get it to focus again. Help if I held it still, probably. There we go. So that first drop, 1.5 times 10 to the negative 19th coulombs. Well, 1.5 is about 1.6. That one has 1 unit of charge on it. This one here has 4 units of charge. 1.6 times 4 is 6.4. This one here is just under 3.2. That's 2 units of charge. This one, again, has gained or lost a single electron, and that's as far as I got. And as for the 2.5, yeah, sometimes things go wrong. I could tell you a couple of ways of messing this up, some of which are the operator's fault and some are not. But anyhow, that's why you need large amounts of data, is so that you can spot things like that as being outliers. How to measure the charge on a droplet? Well, You watch it through the microscope and you turn on the electric field and you watch how fast it moves. We're going to do it in both directions, with the field pushing the drop up and also with the field pushing the drop down. The basic idea behind all the equations is the more charge on the drop, the faster it moves, okay? I mean, you have to do other things like determine the size and mass of the, well, if you know the size, you know the mass, because you can look up the density of the oil. But you have to find the size of the droplet and some factors like that. But in the end, what it comes down to is the more charge, the faster it moves. So we get the charge from the speed that it moves with. How fast does it go up? How fast does it go down with the field on? And then the last thing I'm going to do with each drop is turn the field off and watch how fast it falls under its own weight. Now, this is not free fall, okay? We're not looking at accelerated motion. It's exactly the opposite. These droplets reach a terminal velocity pretty much immediately after you turn them loose. And so they're moving. You see, you've got gravity pulling one way, but you've got air drag pulling the other way, and they cancel each other out, so it moves with a constant velocity. So you watch how fast they fall, and that tells you, well, it tells you how heavy the drop is, or it tells you how big the drop is. Like I said, knowing one is knowing the other, because the density times the volume gives you the mass of the thing. So the bigger they are, the heavier they are. It's pretty much the same measurement. So anyhow, that's what you're going to watch me do here. We'll get this thing going, and we'll get an oil drop and watch it go up and watch it go down and watch it go up, or no, other way around. You start out with it going down, and a couple times with the field on, and then turn off the field and watch it fall under its own weight. Put all the data in the spreadsheet. The spreadsheet does the calculations, which are explained in the directions, which you are supposed to explain back to me in your write-up. And that's pretty much it. Now, what we used to do is I would just have somebody look in the microscope with a stopwatch in their hand. And, oh, you always complain. What I eventually did just a couple of years ago is I bought these video cameras, okay? They're sensitive, low light types of things that that way you can run the image through to this computer monitor here. It turns out that those little numbers on the bottom of the screen that tell you how many minutes you are in the video, it took me a while to figure this out, but they're not particularly accurate. I'm not entirely sure what's going on, but I think maybe, don't quote me on this, but I think maybe the number of frames per second that thing uses to make a recording may vary depending on the light conditions. In low light, it has to make a much longer exposure. And so anyhow, what I eventually did is, at the same time I was making some recordings, I timed it with a stopwatch and found that, sure enough, because, you know, last year the students were getting some kind of not that great results. And so that is the reason why. Let me go over here. The thing I wanted to explain is this fudge factor I stuck in the front here, this 1.15. Where that comes from is the thing I was just talking about. That you see, the times in the spreadsheet are read off of the video playback, okay? But when I compared that to a stopwatch, I found out that the times I was getting that way were on the short side. And this is the this is the ratio of the times measured with the stopwatch to the time measured off the video. This converts video time into real world time as measured by a stopwatch. So that's where the 1 point, and that same factor of 1.15 is in all three of these time columns. So that's, like I said, full disclosure on what I was doing there. Okay, I think that's all the background information. I'm only going to make you watch me run through one trial on this thing because it's repetitive anyhow. We just do the same thing over and over again. But there are the grid lines in the eyepiece of the microscope. See, I've got the camera snuggled right up to the microscope, looking right into it. And what you're seeing on the video screen here is what you would see if you got, or more or less it's kind of blown up. If you actually look into the eyepiece, you can see some more of what's around the edges here. The video camera gives you somewhat of a restricted field of view. And I've got the stick shift here set for field off. Now, there's a little lever on the side of the apparatus here, and it's got three positions. This opens things up, so the middle position there, that opens it up where you can spray the drops in. Once you spray the drops in, you're supposed to push the lever over to where it says off. And that may or may not, remember there was that one trial where the results didn't come out very well? I forgot and left the lever in the open position. I'm not sure if that creates some sort of updraft that affects the results, but that is one thing I know I did wrong in that one that didn't come out as close as the others. Anyhow, there is a third position, but we aren't going to use it. Maybe I won't take the time to explain what it does because we're not going to do that anyhow. And what have we got? We've got a bunch of, and there's a big one. We don't want to get involved in that. Okay, what about that one? That one's not so bad. We can see it pretty clearly. Of course, that means it's bigger, but that's probably all right. And it moves fairly slowly, indicating it probably has a fairly small amount of charge. So we'll get it up in the top of the picture here and click on record, and I need to get it back up to the top again. And here we go. Now it's going down pretty quick. I'm watching this one right here. And then back up. Yeah, it's a heavy one. Bright goes with bigger, bigger goes with heavier. It's a heavy one, so the speed that it goes down is a lot faster than it goes up. That's once each way. And down, and start to look fuzzy. I'd better tweak the focus or it might disappear on me. That makes it worse. Okay, well, then we just live with it fuzzy, hopefully. Yeah, it's kind of coming back. And here, I put the switch in the neutral position. We let it drift down under its own weight. Hopefully it doesn't disappear. Sometimes the oil drops can drift out of the light before you're done, which makes you want to pull your hair out. And you can still just barely see it. Okay, good enough. We'll stop the recording there. and it wants me to give it a name. And I've just been naming it with which line on the spreadsheet it goes with. This will be on line 7 of the spreadsheet. So that's what I'm going to call the file. Okay, and we can get out of this software. Now, what seems to work as well as anything for the playback, I should aim this a little lower, is just some of the standard software that, come on, focus, thank you. We're just going to go down, standard software that comes with Windows. Just going to go down here to the lower left, click on that, and we go on down to where it says Photos. You can look for that under P. And you can, actually you can do some simple video editing and things like that with this, but here we're just going to use it to play the video back. So new video. And I don't care about naming it. And I called it there, that one there, line 7. Drag it down there. Click on this little thing. Okay. So see, here's where I'm going to get my it's kind of washed out, isn't there? We go. That seriously overexposed. Well, even though you probably can't see it, right down here it says 0.00 right now. There we go. That's the magic angle. And as you go through the video, those numbers increase, and that's where I'm going to get my times from. Okay. So I better not, speaking of time, I should probably not waste a lot of time because I've got a class coming in here before too long. But put this right over here where it's handy. So first trick, I can just unplug that at this point. First trick is to figure out which one of these little dots here I was looking at. We should probably start playing it. That was this one. Okay, that one right there. So back it up a little bit. That's a little too far. Right there. So I want to get it right on that heavy line. And I don't know if it's showing up from your point of view. It doesn't look like it on the monitor there, but yeah, I can kind of see it now. 4.53 seconds. So I'm going to come over here and .53. No, you have to. I made a typographical error. Okay, so that goes there where it says down and then start. And now advance the video. There's my dot right there. And maybe back it up a frame or two. No, that's too far. All right, 11.16 for the end of the first drop. Continue the video. So let's see, it was this one here. So there it is on the, no, a little too far. So there it is on this line, starting back up, 13.3 seconds. And advance the video. And it rises more slowly than it, there it is there. That's halfway. We're going 2 large divisions, 1 millimeter. So that's about the right spot, 27.33. Advance the video. Should probably look at the map. Yeah, I don't know if you can see any of this or not from your, I can get a little closer to the camera. A little further. Nope, back up. Guess it's on the line there, 29.13. Down to start. And then there it goes down again. Okay, so there it is on that bottom line at 35.46. We'll continue with the video and time it going back up again. Starting there, 37.13. And run it forward. Does that actually show up? Oh yeah, you can see that on the monitor. That's the one I'm watching right there. Halfway up. Back up a little bit. 51.8. So let's see if I can mess this one up. We've got basically 37 to 52. That's about 15, isn't it? And the first time, 13 to 27. That's about 14, but I'm rounding the numbers off, and they're good. They're close enough. So we've got some fairly consistent numbers, and then it drops under its own weight, starting there, 53.5. And run it forward. It's right there. That's halfway. Yeah, here's where it started getting out of focus on me, but you can still kind of see it. Okay, there it is. Yeah, it's on the bottom line about there. So 1 minute, 17 seconds. In other words, 77 seconds. And that fills in that line on the spreadsheet. So now here's the part where we find out what kind of result we got. And we have to scroll over to the last column where it gives the charge on the droplet. And it's this one right here. 4.65. See that? Times 10 to the negative 19th, which is pretty, 4.65 is pretty close to 4.8. We've got 3 units of charge. 1.6 times 3 is 4.8. So there again, like almost all the other trials, a multiple of the same basic unit. But it's a nice way to display the results. Like it says in the directions here, if you had, a couple dozen data points instead of just 6 of them, you put them on a histogram, kind of like that. And that is a nice visual way of representing, and that's kind of out of focus, but you can kind of see that yeah, there we go. That's what's supposed to happen, that the data clumps up around multiples of E, and the spacing between the clumps is what tells you the elementary charge. For the first trial, that rounds off to 1.51. These are all times 10 to the negative 19 coulombs. The second one, if I can manage to hold the camera still, keep it focused, 6.48. The third one is the one where I left the switch in the wrong position, which may or may not have created a problem, but that's the one that's kind of an outlier, 2.52. And then we've got a 3.08, a 1.48, and the one that you watched me do in detail, 4.65. And that, I think, is about all I need to put into the recording for this.